Hello again and welcome to the fifth video in our normal distribution revision. We're going to look at hypothesis testing, which some people find a little bit more tricky, but I'm here to kind of talk you through it and to help you understand why we do a couple of the things that we do. So this is the bit that confuses some people, okay? The fact that we've now got sigma squared over n, and what's this x bar talking about? Well, I'm going to start just by thinking about a little experiment. We have the numbers from 0 to 9, and people are asked to randomly select numbers and just record what they've got. So if I start by saying a sample size of 3, so people are asked to select 3 numbers at random from this 0 to 9. And I'm just going to have a look at what the mean could actually be. So say you picked 0, 1, and 2. The mean of 0, 1, and 2 is 1. Okay. Now I'm using x bar here. This is what we do. We say that anything with a bar above it is the mean of the sample. I could take another sample and I could have come out with 7, 8, and 9. And x bar for 7, 8, and 9 comes out as 8. Now how does that compare? How do either of these two compare with the sample size, with the population mean? Well, the population mean for this, which we write as mu, that's a population mean as opposed to x bar, which is a sample mean. The population mean is actually 4.5. If you take the mean of all of this, 4.5. So you can see that 1 and 8 seem to be quite far away from the population mean, which means that this sample size of 3, does it represent the sample fully, do we think? There's no right answer to that. But the means are certainly very spread out. Now what we could do is we could take every possible sample size of 3 from these 10 digits, and we could calculate the mean for each one of those. Now how many different ways are there of selecting 3 numbers out of 10? Well, we can use 10, choose 3 for that. We don't have to do this, but there's 120 different sample size 3 combinations. If we worked out the mean of each one of those 120 different combinations of 3, and then we took the average of those means, then the average of those means would be 4.5. And that's really important. The mean of the sample means is the population mean. Now what happens if we increase the sample size? What happens, for example, if I say I'm going to take a sample size of 8? So this time we have to pick 8 numbers up. Well, at the lower end, we could have 0, 1, 2, 3, 4, 5, 6, 7. Okay, that could be my sample. And the mean of this sample is going to be 28 divided by 8, which is going to be 3.5. And say, for example, I took one at the upper end. So I could have 2, 3, 4, 5, 6, 7, 8, and 9. And the mean of this sample would be, just quickly add up in my head, 5.5. There we go. Quick maths. So you can see this time, one of the lowest means we're going to get is 3.5, and one of the highest means we're going to get is 5.5, which are a lot closer to the population mean of 4.5. Now, it's important to note that if we actually looked at every single sample size of 8, there are 45 of them, and we took the mean of each of those sample sizes, and then found the average of those means, we would still get 4.5. What's happened by increasing the sample size is that the variance, okay, how spread out these are, has changed. Increasing the sample size decreases the variance. Now, it therefore also decreases the standard deviation. So there's an inversely proportional relationship going on here. The standard deviation is inversely proportional to the sample size, which is why we take this variance and we divide by the sample size. So let's get into a question and see how it actually all works in practice. We have a company selling fruit juice in cartons, and the amount of juice has a normal distribution with a standard deviation of 3. The company claims the mean amount of juice is 60 mils. A trading inspector receives complaints that the company is overstating the mean amount and wishes to investigate. There's a random sample taken of 16 cartons, and the mean per carton is 59.1 from that random sample. So we have a sample mean, we have a population mean, we have a standard deviation, we have a sample size. What do we do with all that information? Well, the first thing is I'm going to write down the normal distribution of the amount of juice in a carton. So we have 60, which is our mean, and we have standard deviation of 3. So this is our distribution of the amount of juice in a single carton. What we're testing here is the mean. So the means are distributed. Remember, if you took the average of all the means, you get the population mean. And then we're going to have our 3 squared divided by 16, because our sample size is 16. Now, an easier way, or not an easier way, but possibly a more efficient way of remembering this is the same as I've written here, but this variance, this standard deviation bothers me a little bit. I'm going to turn that into 3 over root 16 all squared. Now you can see that 3 over root 16 all squared is the same as 3 squared over 16. Okay, it's just that writing it this way lets me know that I'm inputting 3 over root 16 as my standard deviation into my calculator. It's easy to make a mistake when it's written like this. So this is one of the first things that I would do. So state our hypotheses clearly. The null hypothesis, there's nothing to see here. Everything is as normal. Therefore, the mu for our null hypothesis is that mu is 60. The alternate hypothesis is, what are we actually testing for? Well, if the company is overstating the mean, then that means that the belief is that the mean is less than 60. So this is our hypothesis. We have a significance level of 5%, and this is a one-tailed test. So our test statistic is this 59.1. And all we're testing now is the probability that X bar is less than or equal to 59.1 using this distribution in the calculator. So for the class whiz, we'll go menu 7, normal CD. If you're using the CG50, menu 2, and F5, and then your normal CD. So our lower is our very small negative number, minus 100,000. Our upper is 50.1. Our sigma, now this is where you can get your calculator to use the lifting. So 3 over root 16 we know is just 3/4, but sometimes you can't work them out as easily as that in your head. So we'll just say 3 fraction button square root 16, and your calculator will write that as a decimal when you press equals. And then mu is going to be 60. What's our probability? 0.1151. So now what we do is take this value exactly as we would in the binomial distribution, and we would compare it with the significance level. And we can see that it's greater than the significance level. Now for a result to be significant, we would have to have a probability less than the significance value. So our 2 conclusions then. First one is that there is insufficient evidence to reject H0. Okay, that's our mathematical conclusion. The second conclusion is the contextual. So we just say that there is no evidence that the company is overstating the mean. And we're done. So a lot of it's the same. A couple of bits are different. The different bit, you've got to be mindful of your sample size. Same, null hypothesis, alternate hypothesis. Test your statistic, make your conclusions. So I'm going to have a look at a second example here because we've got a 2-tailed test and we're being asked to work out critical regions. So we've got this machine producing bolts of diameter D. D has a normal distribution with a mean 0.580 and a standard deviation of 0.015. The machine is serviced and we have a random sample of 50 bolts to see if the mean has changed. Okay, the distribution is still normal with a standard deviation of 0.015. So let's turn that into a distribution of sample means. So D with the bar, we've got the same mean, 0.580, and we've got 0.015 over 50 bolts, and 0.015 is squared. And remember, the nice way of writing this so that you know exactly what to type into your calculator is like this. So our null hypothesis is that the mean is 0.580. Our alternate hypothesis this time is that the mean is not 0.580 because it's two-tailed, because we don't know if it's gone up or down. It's just to test whether or not it's changed. We have a 1% significance level, which translates to 0.5% at each tail, because we split that significance level in two because it's two-tailed. And we're asked to find the critical region. So we have a two-tailed test. Okay, so what is it we're actually trying to work out then? We need to test at each tail. We need to find the probability that D bar is less than D equal to 0.005. We're also working out the probability that D bar greater than D equals 0.005. Now I should technically call these D1 and D2. So we'll use our inverse normal calculation and we'll find out what our values are. So we'll go back to menu 7, or again menu 2 and then F5, and we'll use the inverse normal this time. The class whiz always works with the area to the left, so we use our 0.005 for our to the left area. Our sigma value is 0.015 over square root of 50. So we use the fraction button for this. And our mu is 0.580. So this value, D1, is 0.5745. So 4 decimal places. D2, if you're using the class whiz, you're going to find the area to the left. This is the area to the right. So we're going to take that from 1, and our area will be 0.995, and everything else will stay the same. If you're using the CG50, you can just adjust the tail to be right instead of left. So we have 0.5855, both to 4 decimal places. So what is our critical region? Our critical region is going to be for D, the sample, the mean, being less than 0.5745 and greater than 0.5855. So any mean, any sample mean that comes out lower than this number or higher than this number will be significant, and therefore there will be evidence that the mean has changed. So let's look at part B of this question. Mean diameter is calculated to be 0.587. Comment on this observation in light of the critical region. So 0.587 isn't greater than 0.5855. 0.587 is greater than 0.5855. So therefore, just write this number down correctly. So 0.587 is greater than 0.5855. So it is in the critical region, which means we have a significant result. So conclusion 1, this time there is sufficient evidence to reject H0. And then conclusion 2, which is with context, means that there is evidence that the mean diameter has changed. And so again, I want you to look at the fact that a lot of this is very similar to finding critical regions of a two-tailed test for the binomial distribution. Very, very similar. What's different? We're using a normal distribution, and we've had to take into account the sample size here. So the last question that I've got for you is the last question on the normal distribution. And this is one of these questions that tends to trip people up. So we have a random variable normally distributed with a mean mu and a variance sigma squared. Write down the distribution of the sample mean of a random sample of size n. So x is a normal distribution as we know and love. X bar, the means, is a normal distribution where we have to adjust according to the sample size. And that's all that's required for part A of the question. Just this little bit that you know that you're dividing by the sample size. Now, a construction company wishes to determine the mean time taken to drill a fixed number of holes in a metal sheet. Determine how large a random sample is needed so that the expert can be 95% certain that the sample mean time will differ from the true mean time by less than 15 seconds. Assume that it's known from previous studies that sigma equals 40 seconds. Wow. Now, as you know, whenever you're trying to work out mu or sigma or both, or they're unknown, we looked at the Z distribution. And this is no different, all right? First of all, I'm just going to say that X bar distributed normally with mu and 40 squared over n. Okay, that's what I'm just going to write down so that it's out of my head and it's on the page. So this distribution looks like this. Right, there's my mu. Now, what I'm actually going to do is, because I know I have an unknown mean, I am going to use this Z distribution. So the Z distribution has a mean of 0. So Z distributed normally, mean of 0, standard deviation of 1. Now it says the expert wants to be 95% certain that the sample mean time will differ from the true mean time by less than 15 seconds. So what does that look like? So I'm going to draw two lines, one here and one here. And this area shaded in here, this area shaded in here, those are the important bits. Also, the important bit is the shaded in the middle. So we're trying to find this kind of magic number. The shaded area in the middle is 0.95. 95% certain that the sample mean time will differ from the true mean by less than 15 seconds. So over here, this is mu plus 15, and over here, this is mu minus 15. So you can see that this is within 15 seconds of the mean, has to be 0.95. What that means over here is we have 0.025 over here and 0.025 over here. We've split the remaining 5% equally into these two halves because of the symmetry. So we're trying to work out the sample size that's required for this to happen. Now, how do we do it? Well, we use our Z distribution. Again, just to repeat, whenever we've got an unknown mu, we use the Z distribution. So let's concentrate on these two tails. Okay, we've got 0.025 and we've got 0.025. I'll just call this Z1, Z2. Not that it makes any difference because you'll see through symmetry that Z1 and Z2 will be the same size, they'll have the same magnitude, but one will be negative, one will be positive. So we'll use the inverse normal. So what's the probability that Z less than Z1, pardon me, well, it's 0.025, and so we'll use our inverse normal to work backwards from that. So our area 0.025, our sigma 1, and our mu 0. We've got minus 1.960. And that means that Z2 is 1.960 because it's symmetrical about the mean. Now, how does all this work? Are we any closer to finding out what n actually is? Well, first of all, I'm going to remember that this is the way that I prefer to write this distribution. And then I'm going to apply the conversion formula from the standard normal distribution to the real life normal distribution. Now, when we have Z bar and X bar, we're changing it ever so slightly. Instead of dividing by sigma, you're dividing by this, which is our sigma, 40 over root n. Now, I'm just going to use one of my Z values because that's all that's required to find this value of n. You'll see why in a second. So Z is 1.960. X bar minus mu. How do we work that out? Well, X bar minus mu is 15 because we're looking at the sample mean time differing from the true mean time by less than 15 seconds. So X minus mu has to be 15. Okay, the difference between this and this is 15. And then we're dividing by 40 over root n. Now you can see from this that we only have one unknown. It's n. So if we do, best way to work this out, we've got 1.960 multiplied by 40 divided by 15 is the square root of n, just rearranging this equation. And so therefore n, and we'll just do this all in one, we'll type that into our calculators and we'll square it. So we'll do the fraction button, bracket, fraction button, 1.960 multiplied by 40 divided by 15, close bracket, squared, and we get 27.318 ... And so there has to be at least 27.318 in the sample for this to be true. And so n has to be 28. The sample size of 28 is the first number that will return the result that we want. So that's hypothesis testing for the normal distribution and a little bit extra on the end to do with calculations with distributions of the sample mean. Now that finishes my series of 5 videos on the normal distribution. And hopefully you found the thing to just unlock the secret of the normal distribution. Good luck and thank you for watching.